So we're going to use Gauss-Jordan elimination to deduce how these two planes interact. And there are three ways that planes can interact. The first is that they are the same plane, so that they lay directly on top of each other. It's just a different form of the same equation. Or they could be two planes that are parallel, so that they never actually cross each other. Or if they cross, they have to cross like so, and so they will cross on a line that runs to infinity in each direction. So I have this equation up here. So the first thing I'm going to do is pop it into the matrix. So I have a 1 and a 2, a 3 and a 6, and a -2, a -4, and a 4, and an 8. So if I'm trying to do Gauss-Jordan elimination on this, I can see that if I doubled the top row and subtracted row 2, I would eliminate the x. So I'm going to leave R1, and then in this slot I'm going to do 2 R1s, subtract R2. So leaving 1, 3, -2, 4. And 2 of these would be 2, subtract 2 is gone. 2 of these is 6, subtract that, it's gone. 2 of these is -2, -4, subtract that, it's gone. 2 of these would be 8, subtract 8 is gone. So I ended up eliminating an entire row. Oops. Well, if I take that out of the matrix, that says 0 times x, which is 0, regardless of what x is, plus 0 times y, which is also 0, regardless of what y is, plus 0 times z, which again is 0, regardless of what z is, all adds up to nothing. Well, that's always true. And it doesn't matter what your x is, or what your y is, or what your z is. Once you plunk them into that equation, you get 0 as your answer. The only way for the point of intersection between these two planes to be all points is if these are actually the same plane. And so you sort of saw that here, that this equation is just this one times 2. So if this happens to you, you eliminate an entire row, 0, 0, 0, 0, all the way across. These are the same plane. That's the conclusion you will draw from this particular row. So I'm going to erase this, and then we'll try another one that interacts in a different way. So for this one, the same thing. I'm going to put it into a matrix and apply Gauss-Jordan elimination to it and see what happens. So I will have 2, 4 on my x's, -1 and -2, 4 and 8. Perhaps you see what's about to happen. 2 and 5. So if I take 2 of row 1 and subtract row 2, that should eliminate my x's. So I'm going to 2 row 1, subtract R2. I'm going to keep R1, 2, -1, 4, 2. And 2 of these would be 4, -4 is gone. 2 of these would be -2, subtract -2 would be gone. 2 of those is 8, subtract 8 is gone. 2 of these would be 4, 4 subtract 5 is -1. That looks very similar to the last example we did, with one tiny difference. There's a number here. Now that makes a huge change in your interpretation, though. Is if I were to pull this out of the matrix, this says no x's and no y's and no z's is supposed to add up to -1. Well, that's impossible, because 0 times anything is 0, 0 times anything is 0, 0 times anything is 0, and 0 plus 0 plus 0 is not -1. So this actually doesn't work. This is impossible. So what you did was you asked the algebra where those two planes came together, and it said only under these conditions can these planes come together, which are not possible. So you have deduced then that these are parallel planes. So their equations are almost double, right? Double this equation, you get that. If this was a 4, it would be exactly the same plane. So they would be equal everywhere. But because this is offset by a little bit, that vector, right, from nose to screen in the vector equation of the plane has offset it a little bit so that this one is a little bit higher than this one is. So if you get a result like this, all zeros in where the variable should be, and it's equal to a constant, like anything other than 0, you've generated an impossible equation. So those those planes must be parallel. So again, applying Gauss-Jordan elimination to this one, I'm going to pop the coefficients into my matrix, 3 and 1, 2 and -3, -4 and 2, 11 and 4. And you can see just by the numbers of this one, this is not just the first equation scaled up. So there's going to be a more interesting interaction between these two planes. I like this number 1 as my first coefficient, so I'm gonna move it up to the top, and then down here I'm going to do 3 R2s subtract R1 in order to eliminate that x. So keeping R2, it'd be 1, -3, 2, and 4, and 3 of these minus that is gone. 3 of these is -9, subtract 2 is -11. 3 of these would be 6. 6 subtract -4 would be 10. 12 subtract 11 would be 1. That's 2, 6 minus 4 is 10, and 12 minus 11 is 1. Good. Okay. So I'm going to instead of jumping into the matrix here, I'm going to try and eliminate the z value here, because I can quintuple this row and then I'd have a match. I could try to do the y's, but 3 and 11 are kind of awkward, so I'm not going to do that one. So if I were to take, I'm going to do this one step at a time just so it's not quite so confusing. 5 R1s, and then I'm going to leave R2 alone. Be 5, -15, 10, 20, 0, -11, 10, 1. So I'm going to go back to 1/5 of R1 for this row. So I'm just going to this. No, I'm not. That would be counterproductive, because the whole point was to try and eliminate that z. So I'm going to take R1 subtract R2 in this row. 5 minus nothing is 5. -15 subtract -11 would be -4. 10 minus 10 is gone. 20 minus 1 is 19. And R2 would be 0, -11, 10, and 1. Okay. So I've eliminated the z's in this first row, and I've eliminated the x's in the second row. But I'm not going to be able to get rid of the y's. And the reason for that is that I don't have an extra equation. Right? In order to actually properly solve 3 variables, you need 3 equations, and I just don't have enough. So I'm going to be stuck with one of these variables left. So the way I'm going to interpret this, I'm going to build myself the vector equation of a line in 3 dimensions out of this mess. So I just need you to grit your teeth and follow through. This equation up here, that's 5x minus 4y equals 19. And this equation here is negative 11y plus 10z equals 1. So I'm going to notice that I have a y in both of these equations. So I'm going to take those terms with y's in them, I'm going to kick them over to the other side of the equation. So this one will become 5x equals 19 plus 4y. And this one will become 10z equals 1 plus 11y. Okay, so how is that helpful? Well, I'm going to pull a dirty trick here, and I'm going to say that y is equal to 0 plus 1 p. Now that's the same thing as just saying y equals p. So I'm just going to replace the y here with a p and the y there with a p. And it may seem like that serves no purpose right now, but it's going to turn this into a format that I can use just a little later. So if I do that, I'd end up with 5x equals 19 plus 4p's. And then if I divide both sides by 5, I get x is 19 fifths plus 4 fifths of p. So I'm just gonna pop that in here. And if I do the same thing with the z, I'd end up with 10z equals 1 plus 11p. So z is 1/10 plus 11/10 of p. So I could write that in there. So now that that's done, if you look at what I've built here, I have the parametric equations of a line in 3 dimensions. And if you recall back at the beginning of the video, so that there were 3 ways that planes could cross. This is an example of one where the planes intersect in a line. So if I look at this, then my equation would be x, y, z equals 19 fifths, comma 0, comma 1/10 plus p times 4 fifths, 1 11/10. So you can see maybe why I wrote, instead of just y equals p, I wrote it this way, because it separated it out into a starting point and then a thing with the parameter attached to it, so I could write out my vector equation. So when you're working through the practice problems, if you have 2 planes, they are either coplanar, right? You end up with a row of all zeros, so that they're the same plane, or they're parallel, so you'll get 0, 0, 0, and then a number at the back. Or you get to a place like this where you've eliminated one letter in a row and another letter in a different row, and you can't proceed any further. If that's the case, you need to set it up like this and try and extract the equation of a line. So I'll leave you to practice those. Good luck.